let yourself settle in right now. Take a slow breath, letting it move all the way down to the base of your lungs, filling the space beneath your ribs, and then let it go completely. Feel the weight of your body sink just a little deeper into wherever you're resting. Let your shoulders drop. Let your jaw relax. Let the thoughts that followed you here begin to loosen their grip, drifting back just enough to give you some room. There is nothing you need to do tonight except rest and listen. You don't need to remember every number we encounter, because the numbers are so large they exist beyond memory anyway. You don't need to follow every idea to its conclusion, because some of these ideas don't have conclusions. They just keep going, which, as it turns out, might be the most honest thing that can be said about the universe itself. Tonight, we are going somewhere that requires nothing of you except the willingness to drift. We are going to the farthest reaches of what science can tell us about reality, to the edge of the maps, and then beyond the maps themselves. We are going to ask the oldest question human beings have ever carried, a question asked by philosophers who sat beneath stars they thought were fixed in a single revolving sphere, a question asked by astronauts looking out the windows of the International Space Station, a question asked by physicists working in offices surrounded by whiteboards full of equations, and a question that might well be asked by whatever minds exist, if any do, in universe bubbles separated from ours by distances that cannot be meaningfully expressed in human terms. Does space end? Welcome to the Science Pillow, the place where scientific curiosity and the need for rest meet at the perfect hour. If you are new here, this channel is dedicated to exploring the most profound ideas in astronomy, cosmology, natural history, and the mysteries of existence in a way that is gentle, immersive, and atmospheric, designed to carry you into sleep or into rest, while filling your mind with genuine wonder. If tonight's journey into the structure of the cosmos resonates with you, please consider subscribing. It costs nothing, and it means everything to this channel's ability to keep making these journeys. If you feel the love tonight, leave a like as well. Now, take one last long breath. Let your body soften, and let's go. Section 1. The question that has no edge. There is something quietly remarkable about the enduring, unkillable persistence of this question. It appears in the oldest philosophical writings of ancient Greece. It turns up in the theological debates of medieval Europe. It is encoded in the mathematics of general relativity. It structures the research programs of contemporary cosmology, and it surfaces reliably in the minds of ordinary people lying in the dark. In the quiet space that opens up between the end of the day's business and the arrival of sleep, when the noise falls away and there is nothing left between you and the sky. Does space end? The reason the question persists is not that human beings are slow to answer it. It's that the universe seems genuinely, structurally resistant to being answered. Every time we develop the tools to probe a little deeper, a little farther, a little closer to an answer, the universe reveals another layer of complexity, another horizon, beyond which we cannot see, another question nested inside the question we were trying to resolve. Begin with the ancient Greeks, because they are the tradition most directly responsible for the Western intellectual framework through which modern cosmology developed, and because they thought about this question with a seriousness and depth that deserves respect even across 25 centuries. Aristotle, who dominated Western philosophy from his own lifetime in the 4th century BCE through the Renaissance and beyond, argued with great conviction that the universe must be finite. His argument was partly mathematical and partly intuitive. If the stars were scattered outward to infinity, he reasoned, then they could not complete their nightly rotation around the Earth. An orbit, he believed, literally occurred in the span of a single day. No object could traverse an infinite distance in finite time, because infinity cannot be traversed. The universe, therefore, had a boundary, a sphere of fixed stars beyond which nothing existed, not empty space, not void, not darkness, simply nothing at all, no distance, no extension, no thing. For Aristotle, this was not troubling, it was reassuring. A bounded universe was a comprehensible universe, a universe that could be described and understood and placed in its proper relation to the divine. The material world had limits, and beyond those limits was the realm of the unmoved mover, the divine principle that set the spheres in motion without itself being moved. This cosmology was adopted, adapted, and codified by medieval Christian theologians, who found in it a convenient scaffolding for their own conception of a universe with a heavenly beyond. For roughly 1,500 years after Aristotle, the educated world in Europe thought of the cosmos as a set of concentric crystalline spheres. The Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, the fixed stars, nested inside each other like an onion, all rotating around the earth at the center, the whole structure enclosed by the empyrean heaven, the dwelling place of God. The universe was finite, bounded, organized, and centered on the place where human beings lived. Then came Giordano Bruno. Bruno was born in 1548 in a small town near Naples, became a Dominican friar, and developed a habit of thinking that was deeply incompatible with institutional authority in any form. He was brilliant, restless, provocative, and incapable of stopping himself from following an argument wherever it led, regardless of the consequences. In the 1580s, drawing on the work of Copernicus, who had moved the Earth from the center of the solar system to one of the planets orbiting the Sun, Bruno took the next logical step. If the Sun is a star, then the stars are distant suns. And if the stars are distant suns, why should they be fixed in a single sphere? Why should there be any sphere at all? His argument for infinity was essentially the same argument Aristotle had made for finiteness, but inverted. Aristotle said, suppose the universe is infinite, then it cannot be traversed in finite time. Contradiction. Therefore, it is finite. Bruno said, suppose the universe is finite. Then it has an edge, but every edge has a further side. You cannot have a surface without something beyond the surface. Therefore, the universe is infinite, unbounded, without any boundary that could meaningfully be called an edge. And he went further still. Not only was the universe infinite, Bruno argued, it was filled with an infinite number of worlds, other suns with other planets orbiting them, some of those planets perhaps inhabited. There was no center to the universe. Every point in space was, in principle, as central as any other. The universe was not a house with walls and a address. It was more like an ocean that extended in every direction without limit, and humanity was not at the center of that ocean, but simply afloat somewhere within it. In 1600, Giordano Bruno was burned alive in the Campo dei Fiori in Rome. The charges against him were many and complex, involving his views on the nature of Christ, the soul, and magic, and historians still debate which of his heresies was considered most unforgivable. His cosmological views were almost certainly part of the picture. The infinite universe, centerless, boundless, perhaps populated with other inhabited worlds, was profoundly threatening to a theology built around the uniqueness and cosmic centrality of human beings. Bruno was not a scientist in the modern sense. He had no telescope, no mathematics capable of calculating stellar distances, no observational program to confirm his claims. His universe was a philosophical and metaphysical construction, but his intuition, or at least a substantial part of it, was right. The stars are indeed distant suns. Space is indeed vastly larger than anything Aristotle imagined. There is indeed no fixed sphere of stars enclosing everything. And the question of whether space ends, far from having the simple Aristotelian answer Bruno rejected, has turned out to be one of the most subtle, profound, and genuinely difficult questions in all of science. In 1610, just a decade after Bruno's death, Galileo Galilei pointed a telescope at the night sky for the first time and began resolving what had looked like a faint milky smear, the Milky Way, into individual stars. There were more stars than could be counted. The universe was getting bigger. In 1687, Isaac Newton published his laws of gravitation and showed how the same force that pulls an apple to the ground governs the motions of the planets. The universe, at least the part we could see, began to seem mechanical, lawful, and, crucially, describable by mathematics. The question of whether space ends remained open, but now there were, for the first time, tools that might eventually address it. In 1915, Albert Einstein published the general theory of relativity, which utterly transformed our understanding of what space actually is. Space, in Einstein's framework, is not a fixed, featureless container in which things happen to exist. It is a dynamic, flexible medium, a geometric structure that can curve in response to the presence of mass and energy, that can expand or contract, that can, in principle, have different shapes and topologies depending on the distribution of energy matter within it. Einstein's equations could describe a universe that was static, a universe that was expanding, a universe that was contracting, a universe that curved back on itself, and a universe that was infinite and flat. The question of which of these possibilities described the actual universe was now, for the first time, genuinely and rigorously open. In 1929, Edwin Hubble, working at the Mount Wilson Observatory in California, with access to the 100-inch Hooker telescope, the most powerful telescope of its era, made an observation that changed the question permanently. He found that virtually all distant galaxies, which he had only recently established were separate, independent systems of stars far outside our own Milky Way, were moving away from us. And the farther away a galaxy was, the faster it was receding. The universe was not static. It was expanding. The implications of this discovery cascaded through physics over the following decades. If the universe is expanding now, then in the past it was smaller. Run the film of the universe backward, and it contracts. Keep going backward far enough, and everything, all the matter, all the energy, all the space, was compressed into an unimaginably dense, hot state, from which it has been expanding ever since. This was the origin of what we now call the Big Bang theory. And with the Big Bang came an entirely new dimension to the question of whether space ends. Because now space had not just a possible spatial boundary, but a temporal one. The universe had a beginning. There was a moment before which there was nothing, or at least nothing we can meaningfully describe. And if time had a beginning, what was happening before the beginning? The question became not just whether space has an edge you could bump into, but whether space has an origin you could trace back to, and what lay beyond that origin. These questions, the spatial question of whether the universe extends to infinity or curls back on itself, and the temporal question of what preceded the beginning, are still with us. They are the questions we are going to spend tonight exploring. And the answers, such as they are more beautiful and strange than Aristotle or Bruno or even Einstein could have imagined. Rest into it. There is no destination tonight, just the journey. Section 2. What we can actually see, the observable universe. Before we ask whether space ends, we need to establish with great care what we actually mean when we talk about the universe, because this turns out to be one of those cases where ordinary language is subtly but profoundly misleading, and understanding the distinction between what we mean and what we typically say is the key to understanding everything else. There is the universe, and there is the observable universe. These are not the same thing, and the difference between them is one of the most important ideas in all of modern cosmology. The observable universe is the region of space from which light, or any other signal traveling at the speed of light, has had enough time to reach us since the Big Bang. It is not a physical boundary. It is not a place where things are different, where space gets thinner or more crowded or less well organized. It is simply the limit of our view from where we stand in space and time. Beyond the observable universe, everything continues. We simply can't see it, because light from those regions hasn't had time to reach us yet. Think of standing on a gently curving ocean shore on a misty day. You can see clearly for perhaps a mile or two in every direction, and beyond that, the mist closes in and hides the rest of the coastline and the sea. The ocean doesn't end at the edge of your visibility. You know perfectly well that it continues beyond the mist, and you know that a different observer standing somewhere in the mist could see clearly for a mile or two in their own direction, revealing ocean you cannot see from your position. The ocean is continuous. The visibility is limited. These are two entirely separate facts. Our cosmic horizon works on this same principle, but the mist that limits our view is not water vapor. It is something more fundamental. It is time. Light travels at approximately 186,000 miles per second, or about 670 million miles per hour. This is the fastest speed at which anything in the universe can travel. It is also a finite speed. Light is not instantaneous. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at the sun, you are seeing it as it was about 8 minutes ago. When you look at the nearest star system to our own, the Alpha Centauri system, you are seeing it as it was about 4.2 years ago. When astronomers point the Hubble Space Telescope at a distant galaxy and observe it, they are not seeing that galaxy as it is now. They are seeing it as it was millions, hundreds of millions, billions of years ago, depending on how far away it is. The farther you look into space, the further back in time you see. Astronomy is, in a deep and literal sense, archaeology, the excavation not of layers of Earth, but of layers of time. The universe is approximately 13.8 billion years old. This means that light has had, at absolute most, 13.8 billion years in which to travel. Any galaxy or star or structure that lies more than 13.8 billion light years away from us, in terms of the travel time of its light, simply hasn't had time to send its light to us yet. Even if it's been shining since the beginning of the universe, that light is still en route. Consider what this means experientially for a moment. Every observation we make is not just a spatial observation, but a temporal one. Every time you look up at the night sky, you are looking into the past. The Andromeda Galaxy, that faint smudge visible to the naked eye on a clear, dark night, appears as it was 2.5 million years ago, when our ancestors were proto-humans in Africa and the ice ages were beginning their long cycles. The light that enters your eye when you look at Andromeda has been traveling since before humans existed. The galaxy you see is not the galaxy that exists now, but a ghost of it, an echo in light from a time before our species had names or fire or spoken language. Look further, and the time travel deepens. The galaxies we see in the Hubble Deep Field images, some of the most distant objects ever observed, are seen as they were when the universe was only a few 100 million years old, when the first stars had just begun to form. The universe was a different place then. Smaller, hotter, more uniform, still in the process of building its first structures. Those distant galaxies we observe are not galaxies as they are now. They have had more than 13 billion years to evolve since the light we see left them, and they have been carried by the expansion of space to distances far beyond where they appear in the images. There is something vertiginous about this, and something beautiful. The deeper you look in space, the younger the universe you're seeing. The cosmic microwave background, at the very edge of our vision, shows us the universe as a newborn, 380,000 years old before there were any galaxies or stars at all, just a sea of hot, glowing plasma just beginning to thin and cool. The furthest thing we can see is the universe's birth cry, preserved in microwaves, arriving now from every direction simultaneously, filling the sky as a perfect, uniform, ancient glow. But here is where the story becomes counterintuitive in a beautiful way. You might expect the edge of our observable universe to sit at 13.8 billion light-years in every direction. That seems like simple arithmetic. The age of the universe in years, multiplied by the speed of light in light-years per year, gives you the distance. But this calculation assumes that space has been sitting still while light travels through it. And space has not been sitting still. Space has been expanding, and expanding faster and faster, driven by dark energy for the past several billion years. As light from a distant galaxy travels toward us, the space it is traveling through has been stretching beneath it, like trying to walk toward a friend on an escalator moving away from you. The light makes progress, but the destination keeps getting farther. The result is that by the time the light from the most ancient, most distant sources reaches us, those sources have been carried much farther away by the expansion of space than they were when the light first set out. Astronomers account for this expansion when calculating distances in the expanding universe. The result is that the current distance to the edge of the observable universe, where current means how far away those objects are right now, accounting for all the expansion that has happened since their light set out, is approximately 46 billion light-years in every direction. The full sphere of the observable universe is about 93 billion light-years across in diameter. Let's try to build a sense of what 93 billion light-years means. Our solar system, including the entire span of the major planets, fits within a diameter of about 80 astronomical units, where 1 astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles. Neptune, the outermost major planet, orbits at about 30 astronomical units from the Sun. The entire span of our planetary system is, on cosmic scales, an almost absurdly tiny thing. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. To give you a sense of what that means, if the Sun were the size of a basketball, Proxima Centauri would be another basketball roughly 4,000 miles away. The space between stars is mostly, overwhelmingly, almost incomprehensibly empty. Our Milky Way galaxy, this graceful pinwheel of a few 100 billion stars, including our Sun, arranged in a spiral disk roughly 100,000 light-years across, is a thing of mind-bending scale in its own right. Light traveling from one edge of the Milky Way to the other would take 100,000 years. All of recorded human history, from the invention of writing in Mesopotamia to the present day, spans approximately 5,000 years. One crossing of our galaxy takes 20 times longer than all of human civilization. And the Milky Way, for all its grandeur, is just one galaxy. The observable universe contains approximately 2 trillion of them. 2 million galaxies, each one containing anywhere from a few billion to a few trillion stars. The total number of stars in the observable universe, a number that exceeds any useful human analogy, is estimated to be around 10 to the 24th, which is roughly 10 times more than the total number of grains of sand on every beach and in every desert on the surface of Earth. All of this, all 2 trillion galaxies, all 10 to the 24th stars, all the planets and moons and nebulae and black holes and vast empty voids and dense galaxy clusters and filaments of dark matter. All of it fits within the observable universe, a sphere 93 billion light-years across. And yet we don't know if this is the universe, or merely the universe we can see. At the very farthest edge of the observable universe, at the boundary of our cosmic horizon, 46 billion light-years away in every direction, lies the cosmic microwave background. This is the oldest light in the universe, and it represents something extraordinary. The surface of last scattering, the moment when the universe became transparent to light for the first time. For the first 380,000 years after the Big Bang, the universe was so hot and so dense that light could not travel freely. Photons, the particles that carry light, were constantly colliding with the charged particles of the hot plasma that filled everything. The universe was opaque, like the inside of a star or the heart of a sun. No light could escape and travel freely. Then, as the universe expanded and cooled, a phase transition occurred. The temperature dropped enough, to roughly 3,000 degrees, that protons and electrons were able to combine into neutral hydrogen atoms. When this happened, the fog cleared almost instantly. The universe became transparent, and for the first time, photons were free to travel unimpeded through space. All those photons that had been trapped in the fog were suddenly released at once, flooding the universe with light in every direction. That light, that ancient first light of the transparent universe, has been traveling ever since. Over the 13.8 billion years since it was released, it has been stretched by the expansion of space from the visible light of a 3,000-degree gas to the very faint microwave radiation that we can now detect coming equally from every direction in the sky. We call it the cosmic microwave background, or CMB. The CMB, detected by NASA's WMAP satellite and the European Space Agency's Planck satellite with extraordinary precision, looks almost perfectly uniform. The same temperature, within tiny fractions of a percent, no matter which direction you look. The temperature today is 2.725 degrees above absolute zero, a remnant warmth from the birth of the universe. Those tiny fluctuations in temperature, The slight variations of about 1 part in 100,000 are among the most studied and significant measurements in all of science. They represent the seeds of everything that would later form, the regions of slightly higher density that would eventually become galaxy clusters, and the regions of slightly lower density that would become the vast, empty voids between them. Beyond the CMB we cannot see, not because there's nothing there, but because the universe was opaque for the first 380,000 years of its existence. No light from that era escaped. The CMB is the backstop of our cosmic vision, the deepest image the universe can offer us. What lies before it, the first 3 minutes, the first 300,000 years, we can only know indirectly, through theory and inference and the subtle marks those early epochs left on the light we can see. And what lies beyond it, beyond the 46 billion light-year edge of our observable universe, we can only speculate about with the tools of mathematics and the guidance of well-tested theory. The universe continues, almost certainly. But into what kind of space, and for how far, and in what shape, are questions that sit just beyond the reach of any telescope ever built or likely to be built. Section 3. The shape of space, geometry of the cosmos. Let's talk about shape. Not the shape of galaxies or nebulae or the cosmic web, but the shape of space itself. This is a question that sounds straightforward until you think about it carefully, at which point it becomes one of the most subtly challenging concepts in all of physics. When we ask about the shape of space, we're asking something that falls under the mathematical field of geometry, specifically the geometry of three-dimensional spaces that might be curved in ways we can't directly visualize. This is not the Euclidean geometry taught in schools, the geometry of flat planes and straight lines that Euclid codified in ancient Greece. This is the geometry of curved spaces, the geometry of surfaces on spheres and saddles and tori, extended into 3 dimensions and beyond. There are 3 basic geometrical possibilities for the shape of our universe, and they correspond to 3 kinds of curvature: positive, 0, and negative. In a positively curved universe, the most intuitive kind, even if it's hard to visualize in 3 dimensions, space curves back on itself the way the surface of a sphere curves back on itself. On the surface of a sphere, if you draw 2 lines that start out parallel, they will eventually converge and meet. If you draw a triangle, the angles will add up to more than 180 degrees. And if you travel in a perfectly straight line for long enough, you will eventually return to where you started, without ever reaching an edge or a wall. A positively curved universe is finite. It has a definite, though possibly very large, total volume. But it has no boundary, no edge, nowhere you'd bump into the wall and stop. Physicists often call this a hypersphere. It's the 3-dimensional analog of the surface of a sphere. Just as the surface of a sphere is a 2-dimensional space that curves around in a 3rd dimension to close on itself, a hypersphere is a 3-dimensional space that curves around in a 4th spatial dimension, which needn't be a physical dimension we inhabit, just a mathematical direction, to close on itself. Albert Einstein's 1917 model of the universe was a static hypersphere of this kind. Finite, bounded in volume, but without any edges. In a negatively curved universe, sometimes called a hyperbolic universe, space curves in the opposite way. On a surface of negative curvature, like the saddle shape of a Pringle, parallel lines diverge. Triangles have interior angles that add up to less than 180 degrees. A negatively curved universe is generally infinite in extent, space curves away from itself rather than toward, so it keeps going outward without ever closing back. And then there is the flat universe, a space where all the ordinary rules of Euclidean geometry apply. Parallel lines never meet. Triangles have angles summing to exactly 180 degrees. A flat universe, if it is simply connected, that is, if it doesn't have any complex topological wrapping, would be infinite, extending outward in all directions without limit. The question of which of these geometries describes our actual universe is not merely philosophical. It is, in principle, measurable, and the way astronomers measure it is elegant. Einstein's general theory of relativity tells us that the geometry of space is determined by its energy content. Specifically, there is a critical density of mass energy, a particular amount of stuff per unit volume of space, at which the universe is exactly flat. If the actual density of the universe equals the critical density, space is flat. If the density is greater than critical, space curves positively. If the density is less than critical, space curves negatively. Astronomers measure the geometry of space by looking at the patterns in the cosmic microwave background. Those tiny temperature fluctuations in the CMB, those 1 part in 100,000 variations that represent the seeds of structure, have a characteristic size. This characteristic size acts like a known ruler embedded in the distant universe. By measuring how large these fluctuations appear to us, their angular size in the sky, astronomers can determine how they've been distorted during their 13.8 billion year journey. And from that distortion, they can calculate the curvature of the space the light traveled through. The answer, from the WMAP satellite, and then from the more precise Planck satellite, is flat, or so close to flat that we cannot detect any deviation from flatness within the precision of our measurements. Triangles spanning the universe, in the sense of these CMB measurements, have angles that add up to 180 degrees, or so close to it that any departure is too small to measure. The universe appears to be geometrically flat. But here's the crucial subtlety that changes everything. Flatness is not the same as infinite. A flat geometry does not necessarily mean the universe extends to infinity. This is a common misconception, and clearing it up requires thinking about the difference between a space's local geometry, its curvature, and its global topology, which describes how the space is connected on the largest scales. Topology is the branch of mathematics that studies properties of spaces that remain unchanged under continuous deformations, stretching and bending, but not tearing or gluing. Two spaces can have the same local geometry but entirely different topologies. A flat, infinite plane and a flat donut, a shape mathematicians call a torus, have identical local geometry. If you are a small being on the surface of either one, with a limited field of vision, you cannot tell from local measurements alone whether you're on the infinite plane or the torus. The Euclidean rules apply equally in both cases, but they are profoundly different global structures. The plane is infinite, and the torus is finite. Here is how a torus works, because it's important and beautiful, and worth taking a moment to describe. Take a square piece of paper, bend it so that the top edge meets the bottom edge, and tape them together. You now have a cylinder. Then bend the cylinder so that the two circular openings face each other and tape those together. You now have a donut shape, a torus. The original square, with its 4 edges paired up, has become a surface with no boundaries and finite area. In 3 dimensions, The equivalent is called a 3-torus or hypertorus. Imagine a cube. Now, conceptually connect the left face to the right face, so that anything traveling off the left side of the cube immediately reappears on the right side. Connect the top face to the bottom face, so that anything traveling upward reappears from below. Connect the front face to the back face. What you've created is a finite three-dimensional space with no boundaries. A space that, from the inside, looks like it might extend to infinity in all directions, but that actually loops around on itself. In a toroidal universe, if you pointed a powerful enough telescope in any direction, you would eventually be looking at the back of your own head. Light traveling outward would wrap all the way around the universe and come back. Every galaxy would have ghost images, duplicates of itself visible at various distances in different directions, as light takes different paths around the torus and arrives from multiple angles. We haven't found such ghost images, but this could simply mean that the toroidal universe, if we live in one, is large enough that light hasn't had time to wrap all the way around it yet. If the torus is larger than our observable universe, its topology would be invisible to us. We're sitting inside it, unable to see its global shape, just as a person standing in a vast field cannot tell whether the Earth is round or flat without traveling far enough to see the curvature. In 2024, the AHAT Compact Collaboration published research in the journal Physical Review Letters, asserting that prior searches for topology have far from exhausted the potentially significant possibilities. The team, led by cosmologists including Glenn Starkman of Case Western Reserve University, identified 17 distinct flat topologies that the universe might have, and began the painstaking work of searching the cosmic microwave background data for the signatures of each. Their results showed that several previously dismissed topological possibilities had not actually been ruled out. The search for cosmic topology, for the global shape of the universe, is actively ongoing, with new computational tools and new data making things possible that weren't possible a decade ago. What this all means is that we genuinely don't know the shape of space. We know its local geometry appears flat. We know the observable universe is approximately spherical in structure, centered on us. We know the total universe is larger than the observable universe. But whether the total universe is infinite or finite and topologically complex is an open question, one that might ultimately be unanswerable, because any topology larger than our observable universe would leave no traces we could detect. This is one of the deepest and most profound mysteries in all of science. Not just what's out there, but what kind of out there is. Whether the universe goes on forever, or whether it folds back on itself in a vast and beautiful geometry that we are embedded inside, unknowing. Section 4. The Beginning and the Mystery of Before. To understand whether space ends, we need to think carefully about how it began. Because the conditions at the beginning, the earliest moments of the universe's existence, determine much of what the universe became and how large it might be. The Big Bang, as mentioned in our opening, is widely misunderstood. This is not entirely the fault of the name, though Big Bang does invite the mental image of an explosion, something detonating somewhere in a pre-existing space, hurling hot matter outward. But the Big Bang was not this. It was not an explosion in space. It was an expansion of space. All of space. Every bit of room that exists in the universe, all the distances between everything, began at the Big Bang. There was no prior space into which the universe expanded. there was no outside. Space itself, along with time and matter and energy, came into being. This is genuinely difficult for human minds to grasp because we are accustomed to things happening inside a larger context. When something expands, it expands into surrounding space. When something begins, it begins in a pre-existing time. The Big Bang violated both of these intuitions by being the origin of the context itself. What we know about the very earliest moments of the universe comes partly from direct observation. The cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, and partly from physics. The laws of physics as we understand them break down at the extreme densities and temperatures of the first tiny fraction of a second after the Big Bang. We have well-tested physics going back to about 1 microsecond after the Big Bang, reasonable confidence back to about 1/100th of a second, and theoretical frameworks extending back to perhaps 1/1000th of a second. But before that, we reach conditions so extreme that our models fail, and we're honestly not sure what happened. The question of what happened before the Big Bang is not quite the question it appears to be. In general relativity, time is not a fixed backdrop against which events occur. Time is a dimension of space-time, and space-time had a beginning at the Big Bang. There may be no before the Big Bang in the way there is a before Wednesday. The question, what happened before the Big Bang, might be structurally similar to what is north of the North Pole? A grammatically sensible question that is nevertheless empty of meaning, because the concept doesn't apply in the regime you're asking about. But here is where it gets genuinely interesting, and where the theory of cosmic inflation enters the picture. Alan Guth was working at Cornell University in 1978 and 1979, struggling with several deep problems in the original Big Bang theory. Not problems with the evidence for the Big Bang, that was solid. Problems with what the theory implied about the initial conditions of the universe. One problem was the flatness problem. We know today, and cosmologists had reason to believe in the 1970s, that the universe is very close to geometrically flat. The energy density of the universe is very close to what physicists call the critical density. But in the standard Big Bang model, this flatness is extremely unstable in the early universe. A universe that starts out slightly denser than critical will rapidly become much denser, collapsing in a big crunch. A universe that starts out slightly less dense than critical will rapidly become much less dense, expanding too fast for galaxies to form. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, the universe at, say, 1 second after the Big Bang must have been flat to within 1 part in 10 to the 14th power. The slightest deviation in either direction would have produced a universe radically different from the one we observe. This requires an implausibly precise fine-tuning of initial conditions. Another problem was the horizon problem. As mentioned earlier, the cosmic microwave background is almost perfectly uniform in temperature across the entire sky. But regions of the sky that are opposite each other have never been in causal contact. There hasn't been time since the Big Bang for light or any other signal to travel from one side to the other and back. Yet they share the same temperature to better than 1 part in 100,000. In a standard Big Bang without inflation, this is mysterious. How did regions that have never communicated come to be at the same temperature? And there was the monopole problem. Grand, unified theories of particle physics, theoretical frameworks that attempt to describe 3 of the 4 fundamental forces as aspects of a single underlying force. predict that the very early universe should have produced enormous numbers of magnetic monopoles, hypothetical particles that carry a single magnetic pole, either north or south, without the other. The standard Big Bang model predicted so many monopoles that the universe should be flooded with them. But we have never observed a single magnetic monopole. Where are they? Alan Guth's solution to all three problems at once was elegant and radical. He proposed that the very early universe, before the hot, dense Big Bang as we normally describe it, underwent an extremely brief but violent period of exponential expansion. In an almost unimaginably tiny window of time, roughly between 10 to the negative 35 and 10 to the negative 32 seconds after the universe's origin, space expanded exponentially, doubling in size again and again with each tiny fraction of a second. The universe had to double at least 80 times during this period to solve the flatness problem. It may have doubled far more than that. To understand what 80 doublings means, consider the chessboard problem. Place 1 grain of rice on the first square, 2 on the second, 4 on the third, doubling each time. By the 28th square, you'd have more than 100 million grains. By the 64th square, before you even run out of squares, you'd have more grains of rice than there are atoms in the observable universe. 80 doublings of the universe's size would take something far smaller than a proton and inflate it to something larger than the entire observable universe today. The regions we now observe as the CMB, separated by 93 billion light-years in our current universe, began as adjacent, causally connected regions before inflation stretched them apart. This is why they share the same temperature. They were in contact before inflation began. Inflation erased the monopoles by diluting their density so enormously that the chance of there being even one in the observable universe is negligible. And inflation drove the universe to flatness. Any initial curvature was stretched away, just as the surface of a balloon looks flat when inflated to an enormous size. Guth formally published the inflationary model in 1981. It has been refined and developed since then by a number of other physicists, including André Lund at Stanford, who developed a variant called chaotic inflation in 1983. The general framework of inflation is now the leading model for the earliest moments of the universe, supported by the detailed pattern of temperature fluctuations in the cosmic microwave background that have been measured with exquisite precision by the Planck satellite. But inflation also carries a consequence that may be its most profound and unsettling implication, a consequence that bears directly on the question of whether space ends. Most models of inflation, not all, but most, predict that inflation, once started, does not stop everywhere at once. The quantum processes that terminate inflation, converting the energy of the inflating vacuum into the hot particles of the Big Bang, are random and statistical. They happen in some regions at some times, and those regions become universes like ours. But in surrounding regions, inflation continues. And because inflating space expands exponentially, the volume of still inflating space always grows faster than the volume being converted into post-inflationary universes. The result is that the total volume of inflating space is always increasing. Inflation, in most models, is eternal. This is eternal inflation, and it implies that our universe, our entire observable universe plus all the universe beyond our horizon, the full extent of everything that began with our Big Bang, is a single bubble that formed when inflation ended in one small region of a much larger, eternally inflating space. Other bubbles formed elsewhere, in other regions where inflation also ended. Each bubble is a universe unto itself, sealed off from the others by the exponentially expanding space between them, which expands faster than any signal can travel. The question, does space end, becomes, in this context, a question with a different kind of answer than we might have expected. Our universe, our bubble, almost certainly does not end at any measurable distance within the observable universe. It probably extends far beyond our cosmic horizon, possibly to infinite extent within the bubble. But beyond our bubble lies more inflating space, and within that space, other bubbles, other universes, perhaps infinite in number, perhaps with entirely different physical constants, different particles, different laws. Where does that end? In the framework of eternal inflation, it doesn't. It never ends. There is always more inflating space, always more bubbles forming, always more universes crystallizing out of the quantum froth of inflation's eternal expansion. Whether this constitutes space ending depends very much on what we mean by space. If space means the space within our bubble, our universe, it probably doesn't end. If space means the totality of everything that exists in any dimension, the eternal inflationary multiverse, then it ends nowhere, ever. Section 5. The Hidden Universe. Dark Matter and Dark Energy. There is another sense in which most of the universe is hidden from us, and it has nothing to do with cosmic horizons or inflationary bubbles. It is closer to home, much closer. It concerns what most of the universe is actually made of, and the answer is one of the strangest things that science has revealed about reality. Everything you have ever seen, every star in the night sky, every galaxy in the deepest Hubble photographs, every atom in your body, every planet, every moon, every asteroid, every cloud of interstellar gas, every piece of matter you have ever encountered in any form. All of ordinary matter. Matter made of protons and neutrons and electrons. Matter, as described by the standard model of particle physics, constitutes approximately 5% of the total mass and energy content of the universe. 5%. The remaining 95% is divided between two things we cannot see, cannot touch, and do not fully understand. About 27% of the universe is dark matter. About 68% is dark energy. Together, dark matter and dark energy represent 95% of everything. And neither of them has ever been directly detected in a laboratory. We know they exist because of their effects on the things we can see, but what they actually are remains one of the central unsolved mysteries of physics. Dark matter has a longer history in cosmology. It was first proposed in the 1930s by Swiss astronomer Fritz Zwicky, working at Caltech studying the Coma Cluster, a dense collection of more than 1,000 galaxies about 330 million light-years from Earth. Zwicky measured the velocities of galaxies within the cluster and applied a theorem from classical mechanics, the virial theorem, to relate those velocities to the cluster's mass. The mass implied by the velocities was many times larger than the mass implied by the brightness of the visible galaxies. Something was adding mass without adding light. He called it dunkel materie, dark matter. Zwicky was largely ignored. His result was dismissed as probably an artifact of measurement errors or incomplete understanding of the cluster's dynamics. Decades later, in the 1970s, American astronomer Vera Rubin was studying the rotation of individual galaxies. In a galaxy rotating under gravity, you would expect stars near the center to orbit quickly. They're close to the bulk of the gravitational pull, and stars near the outer edges to orbit more slowly, the same way inner planets orbit the Sun faster than outer planets. But Rubin found something completely different. Across galaxy after galaxy, the rotation curve, the graph of orbital speed versus distance from the center, was flat or even slightly rising at the outer edges. Outer stars were orbiting at roughly the same speed as inner stars. This should not happen if the only mass present is the visible stars and gas. The only explanation that fits is that galaxies are embedded in enormous diffuse halos of invisible matter, halos that extend far beyond the visible edge of the galaxy and contribute substantial gravitational pull. This dark matter doesn't shine. It doesn't emit radio waves or X-rays or any other radiation we can detect. But its gravity is real and its effects are measurable. Vera Rubin's discovery provided the most compelling early evidence for dark matter, and her work, done at a time when women faced extraordinary obstacles in professional astronomy, stands as one of the great contributions to 20th century science. Today, the evidence for dark matter is overwhelming and comes from multiple independent directions. We see its gravitational lensing effects, the way massive concentrations of dark matter bend the path of light from distant galaxies, creating distorted arcs and rings in deep telescope images. We see it in the large-scale structure of the cosmic web, the pattern of galaxy clusters, filaments, and voids that spans the universe could not have formed from the gravitational attraction of ordinary matter alone, because ordinary matter would not have clumped quickly enough. Dark matter, which was already collapsing into halos in the early universe, while ordinary matter was still prevented from clumping by radiation pressure, provided the gravitational scaffolding into which ordinary matter later fell. The most dramatic direct evidence for dark matter comes from observations of the Bullet Cluster, discovered in 2006. The Bullet Cluster is two galaxy clusters that have collided and passed through each other. In the collision, the hot gas of each cluster, which makes up the bulk of each cluster's ordinary matter, was slowed by friction and remained roughly where the two clusters intersected, visible as a bright X-ray source. But the dark matter halos of the two clusters, which don't interact with ordinary matter, through any force except gravity, passed through each other unimpeded and continued on their respective trajectories. The result, visible through gravitational lensing, is a cluster system where the visible matter, the hot gas, is located in the center, and the dark matter is displaced to either side, exactly as one would expect if dark matter is real, collisionless, and interacts only through gravity. We know dark matter exists. We just don't know what it is. The leading candidates are hypothetical particles. Weakly interacting massive particles, or WIMPs, were for many years the most popular candidate. Heavy particles that interact only through gravity and the weak nuclear force, which would have been produced in the correct quantities in the hot early universe. Experiments like the Large Underground Xenon Detector, the Pan-Day-X experiment, and the Xenon 1T experiment have searched for WIMPs with extraordinary sensitivity and found nothing yet, casting doubt on the simplest WIMP models. Other candidates include axions, extremely light particles originally proposed to solve a problem in quantum chromodynamics, sterile neutrinos, and primordial black holes. The search for dark matter is ongoing, and it represents one of the most urgent frontiers in physics. Dark energy is even more mysterious and more consequential for the large-scale fate of the universe. Dark energy was discovered in 1998 through observations of Type 1 supernovae. a particular kind of stellar explosion that occurs in binary star systems involving a white dwarf, and that always explodes at roughly the same absolute brightness. This makes them useful as standard candles, objects of known intrinsic brightness that can be used to measure distances across the universe by comparing how bright they appear to how bright they actually are. Two independent teams, the Supernova Cosmology Project led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team led by Brian Schmidt and Adam Rice, were measuring the expansion history of the universe using these supernovae. The expectation, going into the research, was that the expansion of the universe would be decelerating, slowing down over time, pulled back by the gravity of all the matter the universe contains. The teams expected to measure by how much it was decelerating. What they found instead was that the expansion was accelerating. The universe was expanding faster than it did in the past, not slower. This was so unexpected that both teams spent considerable time checking for errors. Finding none, they published their results, and the discovery shook cosmology. Something was pushing the universe apart against the pull of gravity. Something was adding energy to the expansion rather than taking it away. Something that was, apparently, a property of empty space itself. A pressure inherent in the vacuum that accelerated as the universe grew, because as the universe grew there was more space, and with more space came more of this mysterious vacuum energy. This is what we call dark energy. The simplest model, the one that best fits all available data, treats it as a cosmological constant, a fixed, unchanging energy density of the vacuum, the same everywhere and always. In Einstein's original equations of general relativity, there was a term for exactly such a thing, which he called the cosmological constant, and introduced in 1917 to hold his model of a static universe in balance. He later removed it when Hubble demonstrated the universe was expanding, calling it his greatest blunder. It turns out it was not a blunder, or at least something very like it appears to be real. The cosmological constant is, however, profoundly puzzling to theoretical physics. When quantum field theory, our best description of the subatomic world, attempts to calculate the energy density of the vacuum, it gets a number that is approximately 120 orders of magnitude larger than the observed value of dark energy. This is the worst prediction in the history of science by any measure, and it suggests that something deep is missing from our understanding of how quantum mechanics and gravity relate to each other. Dark energy constitutes 68% of the total energy content of the universe. It currently dominates everything else combined. And because dark energy is a property of space itself, increasing as the volume of the universe increases, its influence grows over time, while the influence of matter and dark matter dilutes as the universe expands. We are living at a point in cosmic history when dark energy has recently begun to dominate, when it is actively accelerating the expansion of space, pushing galaxies apart faster and faster, expanding the universe in a way that may last for trillions of years. Section 6. Beyond the Horizon. We've established several things. The observable universe is a sphere 93 billion light-years across, and it is almost certainly not the totality of all that exists. The universe appears flat, at least within the observable portion, but this flatness is consistent with either an infinite universe or a very large finite one. The theory of cosmic inflation suggests that our universe is one bubble in an eternally inflating sea of space, with other bubble universes forming and evolving in the unreachable beyond. Dark energy is accelerating the expansion of our universe, which means the boundary of what we can ever observe is actually shrinking over time. Now, let's think explicitly about what might lie beyond the horizon. Within the framework of inflation producing a single, very large universe, without the multiverse complication, what lies beyond our 46 billion light-year horizon is probably more of the same. More galaxies, more dark matter, and dark energy, more stars and planets, all following the same laws of physics we observe here. This is the picture that many cosmologists consider the baseline assumption. The universe is vastly larger than what we can see, possibly infinite, and it looks roughly similar throughout on the largest scales. In this picture, a curious thing follows almost immediately from the combination of infinite space and the finite number of ways matter can be arranged in any region. If space is truly infinite, and if the laws of physics hold everywhere, then the number of possible configurations for any given volume of space, say, a region the size of our observable universe, is very large but not infinite. Quantum mechanics places a firm upper limit on the number of distinct states any physical system can occupy. For a volume the size of our observable universe, this number is estimated as 10 to the power of 10 to the power of 122. This is an incomprehensibly large number, but it is finite, and in an infinite universe, a finite number of possible configurations means that every configuration must eventually repeat, infinitely many times. There must be, in an infinite universe, infinitely many regions of space that are exact duplicates of our observable universe. The same distribution of galaxies, the same stars, the same planets, even the same people having the same conversations and asking the same questions. Not just similar, but identical to the last particle. And, beyond those, regions where things went slightly differently, regions where you made different choices, regions where the Earth formed around a different star, regions where the Milky Way has a slightly different shape. The cosmologist Max Tegmark has explored this implication with rigorous seriousness, arguing that it follows as almost an inevitable logical consequence of an infinite universe with a fixed set of physical laws. The nearest exact duplicate of our observable universe, the nearest cosmic copy of everything you can see, would be so far away that expressing the distance in light years would require more digits than there are atoms in the observable universe. It is, for all practical purposes, absolutely, permanently beyond any possible communication or contact. But in an infinite universe, it exists. This is a deeply strange implication, and not everyone finds it intellectually satisfying. The physicist and philosopher Roger Penrose, among others, has argued that the implications of infinity in physics need to be handled with greater care than physicists sometimes afford them. Infinity is a mathematical concept that can be manipulated in equations, but whether it corresponds to anything physically real is a question that deserves genuine scrutiny. Now, layer on the multiverse implied by eternal inflation, and the strangeness deepens considerably. In the inflationary multiverse, our universe is a single bubble in an eternally inflating background. The inflation that produced our bubble ended through a quantum process, a random transition from the energy state of the inflating vacuum to a lower energy state, the way a supercooled liquid can spontaneously crystallize. But quantum transitions are statistical. They can settle into different outcomes in different places. The energy state that inflation ends in, the ground state of the vacuum in each bubble, need not be the same from bubble to bubble. And the fundamental constants of physics, the masses of particles, the strength of the fundamental forces, the cosmological constant, the number of spatial dimensions, may depend on the ground state of the vacuum. This means that different bubble universes in this framework can have fundamentally different physical laws. A universe where gravity is 10 times stronger than ours. A universe where the electron has a different mass, making atoms unstable. A universe where the cosmological constant is large enough that it prevents any structure from forming before the universe flies apart. A universe where there are 4 large spatial dimensions rather than 3. Universes so alien that the chemistry of life as we know it is simply impossible, where no stars shine, where nothing organizes itself into structure. Leading cosmologists including Alan Guth, Andrei Lund, and Alex Vilenkin have argued that eternal inflation and the multiverse it implies are not merely speculation, but are nearly inevitable consequences of the well-tested inflationary framework. Guth has said directly that it is hard to build models of inflation that don't lead to a multiverse. The question of whether the multiverse is science, whether it is testable, falsifiable, and therefore genuinely part of the scientific enterprise, is actively debated. The physicist Paul Steinhardt, who was one of the developers of inflationary theory, has become one of its most vocal critics, arguing that a theory that predicts everything effectively predicts nothing, and that the beauty of a physical theory lies in its ability to make sharp, testable predictions that could in principle turn out to be wrong. A multiverse with every possible set of physical constants can always accommodate any observation we make, simply by noting that we happen to live in a bubble where the constants have the observed values. It cannot be proven wrong. Others, including Linda, argue that the multiverse is a genuine scientific hypothesis, because it makes statistical predictions about what kinds of universes are likely to be inhabited by observers like us. Predictions that, in principle, could be checked by further understanding of the distribution of physical constants across bubble universes. This is an ongoing and genuinely difficult philosophical discussion about the nature of scientific knowledge. There is one observational handle on the multiverse that is at least in principle testable. If our bubble universe collided with another bubble universe during the very early inflationary phase of our universe's history, that collision might have left a faint, distinctive pattern in the cosmic microwave background. A circular ring of slightly different temperature, or a localized anomaly in the CMB that stands apart from the background fluctuations. Researchers have searched for these collision signatures in the WMAP and Planck data. No definitive evidence has been found, but the search hasn't definitively ruled out all possible bubble collision signatures either. And so we come back to the question we started with, now enriched by everything we've explored. Does space end? Within our observable universe, no, space does not end at any horizon we can see. Beyond the observable universe, space almost certainly continues, probably much farther, possibly to infinite extent. Beyond our bubble universe, if eternal inflation is correct, there may be more inflating space and more bubble universes, extending without limit, a true infinity of worlds. Whether any of this constitutes space ending depends on whether we consider inflation's unobservable region to be the same kind of space as the space we inhabit. The honest, rigorous, fully considered answer is, we don't know. Not because we haven't thought about it hard enough, but because the universe seems to have built into its structure a fundamental limit on what can be known from within it. Section 7. The Fate of Space and Time. We've looked outward and tried to find the edge of space. Now let's turn forward and look for the edge of time. Does the universe have an end as well as a beginning? And if so, what does that end look like? The answer, as with so much in cosmology, depends on quantities we don't yet know with certainty. Specifically, the true nature and behavior of dark energy. But we have a leading scenario, and it is called the Big Freeze, or the heat death of the universe. It is a scenario that unfolds across timescales so enormous that every concept of long we normally use is rendered quaint. We are currently living in what astronomers call the stelliferous era, the age of stars. The universe around us is lit by the thermonuclear fusion happening in the cores of hundreds of billions of stars in each of roughly 2 trillion galaxies. Stars are being born and dying. Galaxies are colliding and merging. Structure is still forming. The universe is, by the standards of the long future ahead of it, young and active and full of light. This era will not last forever. In about 5 billion years, our sun will exhaust the hydrogen in its core and swell into a red giant, engulfing the inner planets including Earth, before eventually collapsing into a dense stellar remnant called a white dwarf. This is the fate of most stars. A long, bright life followed by a dimming and a cooling with nothing left but a slowly fading ember of compressed carbon. On larger scales, in roughly 150 billion years, the accelerating expansion driven by dark energy will have carried all galaxies beyond our local group across the cosmic event horizon, the boundary beyond which nothing can ever reach us. The Milky Way will still exist, having by then merged with Andromeda and several other local group galaxies into a single large elliptical galaxy. But looking outward from that merged galaxy, the universe will appear empty. All the trillions of other galaxies will have receded into an absolute darkness, moving away faster than light can bridge the gap. Future astronomers in that galaxy, if any exist, will have no evidence that the wider universe exists. They will look out into emptiness and conclude they inhabit the only galaxy there is. In about 1 trillion years, 1 million years, star formation will have ceased throughout the universe. The supply of cold gas available to collapse into new stars will have been exhausted, consumed, expelled, or spread too thin by the expansion of space. The last stars will be small, cool red dwarf stars, which burn so slowly that the most massive ones can last for up to 10 trillion years before exhausting their hydrogen. But eventually, even the most long-lived stars die. The universe will enter the degenerate era, a dark, cold cosmos populated by the corpses of stars, white dwarfs, neutron stars, black holes, slowly cooling toward the temperature of space around them. Free-floating planets, dark matter halos, the occasional comet or asteroid drifting through emptiness. Over timescales that make the age of the universe today look like a blink, gravitational dynamics will slowly disassemble even the remnants of structure. Stars and galaxies are not perfectly stable. Gravitational encounters between them, over billions and trillions of years, gradually eject most stars into intergalactic space. Galaxies themselves dissolve as their stellar populations drift away. What remains, after 100 quintillion years or so, 10 to the 20th, is a universe in which almost all matter has either been swallowed by black holes or is drifting as isolated stellar remnants through a vast, cold, ever-expanding void. The black holes that form the final anchors of structure are themselves not eternal. In 1974, Stephen Hawking used a brilliant synthesis of quantum mechanics and general relativity to demonstrate that black holes are not perfectly black. They slowly emit thermal radiation, now called Hawking radiation, as a consequence of quantum effects near the event horizon. The rate of this radiation is extremely small for large black holes. So small that a stellar mass black hole would take longer than 10 to the 67th years to evaporate completely. A supermassive black hole, like the one at the center of the Milky Way, or the gigantic black holes in the centers of large galaxies, might take 10 to the 99th years or more. These are, again, numbers beyond any intuitive grasp. But they are finite. And eventually, every black hole evaporates in a final burst of Hawking radiation, leaving behind only stray photons and the lightest particles drifting through an ever-expanding void. After the last black hole has evaporated, in a universe whose age in years would require an exponent with exponents to express, the universe enters the state cosmologists sometimes call the heat death. Not a dramatic hot death, despite the name, but a cold, quiet, profoundly featureless final state. The universe approaches absolute zero in temperature, not quite reaching it. Entropy, the degree of disorder, of randomness, of the diffusion of energy, approaches its maximum, the state in which no energy differences remain, no processes can occur, no work can be done. There is no chemistry, no heat flow, no light, no life, no thought, no structure of any kind. Just an infinitely thin scattering of elementary particles separated by distances so vast that they will never interact again, all moving apart from each other forever in perfect, permanent, frozen disorder. The universe will not end with a bang. If this scenario is correct, and it is currently the most well-supported, it will end with a silence so deep and so complete that the word silence hardly captures it. There are alternative possible fates. If dark energy turns out to increase in strength over time, a mathematical possibility described by the parameter physicists call the equation of state. If it is less than -1, then the expansion of the universe could become so powerful that it eventually tears apart not just the space between galaxies, but the galaxies themselves, and then the solar systems, and then the planets, and then the rocks, and then the atoms, and then the nuclei, in a catastrophic process called the Big Rip. The timeline for this scenario, depending on the exact properties of dark energy, could be as close as 22 billion years in the future or far beyond that. Current measurements suggest dark energy has a value of its equation of state parameter close to -1, the cosmological constant value that leads to the heat death rather than the Big Rip. But the measurements cannot currently distinguish definitively between these possibilities. And then there is the new question raised by the 2025 DESI results. The Dark Energy Spectroscopic Instrument, a remarkably sensitive galaxy survey instrument at Kitt Peak National Observatory in Arizona, has been mapping tens of millions of galaxies to track the expansion history of the universe with unprecedented precision. In early 2025, the DESI team released results suggesting that dark energy might not be constant over time, that its strength may have varied over cosmic history in a way inconsistent with a simple cosmological constant. If confirmed, this could change the picture dramatically. A dark energy that weakens over time might eventually allow gravity to slow and potentially halt the expansion, opening the possibility of a big crunch, a reversal, a collapse back toward the beginning. This would be the most dramatic possible fate, the universe ending as it began, in a state of infinite density, perhaps spawning another Big Bang, perhaps not. The DESI results are not yet at the level of confidence physicists would call a discovery, and extraordinary claims require extraordinary evidence. But they are intriguing, and they remind us that the fate of the universe remains genuinely open, not just philosophically, but scientifically. These are the possibilities. The heat death, the most likely. The Big Rip, a possible dramatic ending. The Big Crunch, now less likely but not ruled out. All of them eventual. All of them real, in the sense that physics takes them seriously and spends serious effort investigating them. None of them soon, on any scale that matters to us or to anything we know about or love. The universe is large, and it is patient, and it has time. More time than we can imagine. Section 8. Living at the center of everywhere. We have traveled far tonight. We've traced the question of whether space ends from Aristotle's bounded sphere of fixed stars through Giordano Bruno's passionate defense of an infinite cosmos, through the discovery of the expanding universe and the cosmic microwave background, through the geometry and topology of space and the theory of inflation, out into the speculative architecture of eternal inflation and the multiverse, forward to the long, cold quiet of the heat death. We've encountered dark matter and dark energy, the invisible structures that together constitute 95% of everything that exists, whose natures remain among the deepest unsolved mysteries in all of science. And now I want to bring you back to something surprisingly intimate, something that lives not at the cosmic scale, but at the human one. One of the most profound facts in all of cosmology is this: every observer in the universe is at the center of their own observable universe. There is no privileged location, no special vantage point from which the cosmos is best observed. Instead, every point in space has its own cosmic horizon, its own sphere of visibility, its own unique and irreplaceable window onto what exists. From wherever you are right now, from whatever small, comfortable, warm place you're lying or sitting as you listen to this, the observable universe extends 46 billion light-years in every direction. You are the center of that sphere. Not because of anything special about you, not because the cosmos arranged itself around your particular location, but simply because the observable universe is, by definition, the region of space centered on the observer. Every observer is the center of the universe they can see. This seems like a minor point, a definitional quirk. But think about it a little longer, and it becomes something stranger and more beautiful. A being on a planet orbiting a star in the Andromeda galaxy, 2.5 million light-years from us, has its own observable universe, also 46 billion light-years in radius, also centered on them, overlapping with ours in large portions but extending in different directions into regions we cannot see. A being in a galaxy at the far edge of our observable universe has its own observable universe, most of which is entirely hidden from us. We are in a small portion of its view. It is in a small portion of ours. And the space we cannot see but it can is vast, and filled with galaxies and stars and structure we will never observe. The universe is not centered anywhere, or, rather, it is centered everywhere. There is a long tradition in the history of science of what historians sometimes call the Copernican revolution, a revolution that is ongoing. Copernicus removed the Earth from the center of the solar system. Harlow Shapley in the 1920s showed that our Sun is not at the center of the Milky Way, but at its outskirts, about 26,000 light-years from the galactic center. Edwin Hubble showed that the Milky Way is not the center of the universe, but one of billions of galaxies scattered throughout space. Each step in this progression seemed to diminish the cosmic significance of humanity. We are not the center of the solar system, not the center of the galaxy, not the center of the universe. We are residents of an unremarkable rocky planet orbiting an ordinary star in a common spiral galaxy, one of 2 trillion galaxies, in one observable bubble of a cosmos that may itself be one of infinitely many. And yet, something remarkable happened, somewhere along the path of cosmic evolution, that we are only now beginning to appreciate in its full strangeness. The universe spent roughly its first several 100 million years in darkness, a darkness that followed the extinguishing of the first light after recombination and preceded the ignition of the first stars in the universe. No eyes saw the formation of the first hydrogen clouds. No minds contemplated the collapse of the first protogalaxies. For hundreds of millions of years, the universe evolved in profound, absolute, lightless silence. Then the first stars lit up. And eventually, after some generations of stellar birth and death and the synthesis of heavier elements, complex chemistry became possible. Planets formed with the right conditions. On at least one of those planets, and almost certainly on many others, scattered across the 2 trillion galaxies of the observable universe, chemistry organized itself into something that could replicate, that could evolve, that could, over billions of years, develop the capacity for consciousness and thought and curiosity. The universe made a kind of thing that could ask questions about the universe. Think about what you are in these terms. You are made of atoms. Every atom in your body was forged in the nuclear furnace of a star. The carbon that forms the backbone of every organic molecule in your cells was synthesized in the cores of red giant stars billions of years ago. The iron in your blood, the element at the heart of hemoglobin that allows you to carry oxygen, was made in the core of a massive star. A star that exploded in a supernova, scattering its elements into the interstellar medium, where they eventually became part of the molecular cloud that collapsed to form our solar system. You are literally made of dead stars. And here you are, made of stardust, lying in the quiet, wondering whether the space you inhabit ends. The universe, which had no capacity to contemplate itself for most of its 13 billion-year history, has spent the last few 100 million years, a tiny fraction of its total age, in the company of creatures that can contemplate it. Through the eyes, the instruments, the mathematics, and the imagination of creatures like you, the universe is examining itself. The cosmos is looking back at the conditions of its own birth, peering into the structure of its own large-scale geometry, asking whether it ends. This is not a small thing. In the entire observable universe, with its 2 trillion galaxies and its estimated 10 to the 24th stars, the emergence of beings capable of this kind of reflection is, as far as we know, extraordinary. It may be common on the cosmic scale, distributed across millions of planets in millions of galaxies. Or it may be rare, a cosmic accident, a statistical improbability that happened to happen here in our small corner of the Milky Way. We don't know. The universe has not yet found a way to tell us. But the fact of it, the fact that you exist, and that you can look up at the night sky with a mind capable of wondering, is itself a kind of answer to the question of whether any of this means anything. The universe does not have opinions about meaning. It does not care whether it ends or extends forever. It does not watch us with interest as we try to understand it. It is not a person or a god. It is simply what it is, vast and old and complex and beautiful in the ways that mathematical structure is beautiful. But you are here, and you care. And that caring, that wonder, that insistence on asking the question even when the question might be unanswerable, even when the answer retreats behind every new horizon you approach, that is something genuinely remarkable. Does space end? The most considered, most rigorous, most honest answer that modern cosmology can give is this. The observable universe ends at a horizon 46 billion light-years away, and beyond that horizon, the universe almost certainly continues for a very long way, and possibly forever. If the universe has a finite topology, if it is a vast torus or hypersphere, it eventually curves back on itself, but without walls or edges, without any detectable boundary. If the universe is infinite, it continues without any end at all. If eternal inflation is correct, beyond the boundaries of our own bubble universe lies more inflating space and more bubble universes in a structure that itself may have no end. And if the universe is heading toward a heat death, then it ends in time rather than space. A final, eternal stillness that is not really an ending so much as a forever. The question does not have a clean answer. It never did. But asking it carefully, following it through all the layers of modern cosmology, has taken us somewhere extraordinary, has shown us the shape of space, the birth of time, the hidden structure of 95% of all that exists, the fate of the cosmos, and the strange, beautiful, improbable fact of being a conscious creature in the middle of all of it. There is something worth sitting with, in the quiet before sleep takes you, in the particular kind of openness that comes when the day is done. The universe's unanswerability is not a failure of science. It is science working perfectly. The reason we can say with confidence that we don't know whether space ends is because we've thought about the question so carefully, built such precise instruments, developed such powerful mathematical frameworks, that we can now see exactly where our knowledge ends and the unknown begins. The edge of our knowledge is not a wall of ignorance but a frontier of extraordinary clarity. We know precisely what we don't know and why we don't know it, and that is a profound achievement. Earlier generations of humans who asked this question didn't know where the edge of their knowledge was. They thought Aristotle's sphere of fixed stars might actually be the boundary of existence. They didn't know about galaxies, about the expanding universe, about the cosmic microwave background, about dark matter and dark energy, about inflation and the multiverse. They were asking the same question we are asking, but without the tools to know how deep the question went. We know now. We know the question goes all the way to the bottom. We know it doesn't have a resting place. And we know that this is not a deficiency in the question or in the people asking it, but a reflection of the genuine, astonishing depth of the reality we inhabit. The universe is bigger than we thought. Bigger than Aristotle thought, bigger than Bruno thought, bigger than Einstein thought when he wrote his first cosmological papers. Every generation of scientists has found a universe more vast than the generation before had imagined. There is no reason to expect this to stop. The universe seems to have infinite depth, infinite layers of discovery waiting for the instruments and the mathematics and the imagination to be developed sufficiently to probe them. The question of whether space ends may be answered someday in ways we cannot currently imagine, using tools and concepts that don't yet exist. Or it may remain open forever, a question at the permanent frontier of the knowable. Either way, it is a beautiful question. And you, lying here in the dark, asking it, even silently, even just by letting these words move through your mind, are participating in one of the oldest and most fundamental things that minds like yours do. You are wondering. And wondering in a universe that mostly doesn't is an extraordinary gift. Rest now. Let it all go. The cosmos will be there in the morning, exactly as large and old and mysterious as it is right now, waiting patiently for the next question. Closing. So here we are, at the place where the journey gentles down and the questions can rest. We have traveled from Aristotle and Giordano Bruno to the Hubble Space Telescope and the Planck satellite. We've visited the observable universe with its 2 trillion galaxies and its 46 billion light-year horizon. We've sat with the question of the universe's shape. Flat or curved, finite or infinite, simply connected or topologically complex. We've gone back to the first fractions of a second of inflation and tried to see what might lie before and beyond. We've met dark matter, the gravitational scaffolding of the cosmos, and dark energy, the mysterious engine of acceleration, and we've accepted that together they constitute 95% of everything while remaining largely unknown to us. We've looked forward to the long, quiet future, the era of cooling stars, the era of wandering remnants, the era of evaporating black holes, the era of heat death, or perhaps, if dark, energy has something unexpected in store, the era of the big rip or even a big crunch. And we've come back to you, lying in the dark, made of atoms forged in the hearts of stars. A temporary arrangement of matter that the universe has somehow organized into something capable of asking whether it ends. It probably doesn't. At least, not in any way we can see or measure or point to. The horizon is real, but it is the limit of our vision, not the limit of what exists. Space, as best we can tell, keeps going, into the unobservable, into the topologically complex, into the inflationary beyond, into the bubble universes of a multiverse so vast that our entire observable universe is a speck within it, or into simple, beautiful, infinite flatness. We don't know which, but in either case, the space goes on. What doesn't go on is you, being awake, and that's perfectly fine. That's the point. If tonight's journey left you feeling something, wonder, or calm, or the particular kind of peace that comes from recognizing how vast and strange and indifferent the cosmos is, how impossibly small and yet strangely significant the fact of being here is, then please let that feeling carry you the rest of the way toward sleep. You have earned it. If this channel is something you'd like to return to, please subscribe. It's free, and it genuinely helps the Science Pillow reach the people who might need exactly this kind of rest. If tonight was particularly meaningful to you, a like means a great deal. Sleep well. The universe will still be here when you wake. All 93 billion observable light years of it, and everything beyond. Dark and vast and patient and old, waiting without expectation for whatever comes next.